So let me do this. Let's go to Q&A session. And again, Greg, I can't thank you enough. That presentation was absolutely remarkable and so in depth, so comprehensive. Thank you so much for pulling all that together. This is why I love recording these, because people will go back through that and review that, right? And that's the archival aspect of what we try and do. So okay, so in terms of questions, let me see. It is Option Y on Mac or Alt Y on Windows. Please raise your hand. I know that we have tons of questions. With big presentations like this, sometimes there's so much material that people are kind of slow while they're organizing their thoughts. And let me see. There's Harold. Harold, go for it, sir.
Great presentation. A lot of food for thought. I mean, it was a banquet. So my number one question is the one I have. Can anybody hear me?
Yeah, I can. Your mic is a little faint. Harold, your old desktop mic seemed like it worked better. Do you think you could switch back to that?
Okay. Yes.
Yeah, that right there. That's perfect. That's perfect.
My question for you is, you know, I mean, you put a banquet of food for thought there. I mean, there is a lot that some of the theoretical physicists that deal with that would love that. But my question for you is this: have you mixed it up, you know, speculating the area, like with the warp drive? You know, Alcubierre warp drive, it uses, you know, the relative time in Einstein equations. And I wonder, have you done any speculation, any wonder in that area on how with compressed time, mix it up, you know, apply to warp drive physics?
Right. Can you hear me, Tim? Are we good?
Yeah. No, you sound great.
Good. Okay, good. And the mic was much better after changing the whatever you did to change the mic. It was great. Let me answer that question this way. I am awed by the ideas that come forward in groups like APEC and others, or really APEC in particular. They're just amazing. You talk about warp drive, which is a fascinating subject in and of itself. I can only hope it's true. I think that is fantastic. And but to answer your question specifically, I have not incorporated that technology or tried to incorporate that technology into my presentation or into this presentation in particular. That's a great thought. It's food for thought, and it's something that would be fun to take a look at. How would warp drive relate to this? I received an email earlier this morning, which is great. You know, it's one of those emails that we hope you're not feeling the pressure, but hey, you know, I had a couple of questions. And the fact is that basically what this person was saying, and it was an excellent email. It was really well written. They critiqued the presentation essentially that was posted to Figshare about noon, Central Time. They critiqued it in detail, and essentially they were asking how this fit into several leading paradigms in foundational physics. They talked about pilot wave theory, and they talked about other theories, and it's remarkable. It's such a broad subject that it would be great to take each of these and look at how they might fit within the framework of a 10-dimensional time. But I have not, to answer your question again, have not gone through and tried to look at warp drive. I'm amazed by that. It's an amazing subject, and I fully support everyone that is working on that technology. It's remarkable.
Well, the other question I have is that I have read some paper speculation about actually gravity. It's time, you know, extremely related to time. Now you have compressed time. How would that basically, you know, would that create a new form of gravity from what you have speculated? Have you thought how would it alter gravity, you know, like in Kaluza physics, the fifth dimension, the gravity said to be is so weak in our universe, in our space-time, because gravity penetrates all dimensions and is diluted. Now, from your viewpoint, discussing, you know, compressed time, propulsion, how would that alter gravity? You know, how would that apply, especially since you mentioned application in 10 dimensions?
Right. I think, in fact, let me look at this just briefly. There was a paper written on a 10-dimensional space-time resulting in 24-dimensional Leech lattice, which I thought was an interesting article. And let me find the name on this quickly. It's Potter, I think, is the one that wrote this. This was in 2005. And then there was another article written called Self-Duality and Into String Magic. Basically, it's an article written regarding the concept of a 24-dimensional model in string theory. Now, what caught my attention there was the fact that what I'm talking about, the model that I presented this morning, fits well into a 24-dimensional theory. I mean, it's very interesting how those can work together. And it's interesting that one is a string theory paper and the other may be more related to a loop quantum gravity perspective. Bottom line, it doesn't change gravity. And it may just be, because I believe gravity, it's not going to change it, but it may be a fresh look of how it might be explained. If we can compress time, then intuitively, I'm thinking that, yes, that's going to amplify gravity. And it would do it through a quantum effect. Now, don't ask me how to define that exact quantum effect. I don't know. It's going to take someone a lot smarter than I am to be able to go through and say, all right, this is exactly the mechanism in which gravity would be amplified. I'm looking at this intuitively from the aspect of gravity because I haven't done a lot of work on this as far as gravity is concerned. How might we be able to identify exactly how gravity is amplified? I don't know. And that's something that needs to, I've got some ideas, but it's something that's going to have to be formulated in a more formal way.
Well, that's good. You know, I agree with that statement that you say. So when you start speculating about how will we transform with change gravity, you said it doesn't change it, but then you should add how will it react in terms of anti-gravity, since, you know, we all know about gravity. There's a lot of speculation about anti-gravity. As you are explaining compressed time, time is related to gravity. Therefore, how would that relate to anti-gravity? So in the future, if you have another presentation, I hope you bring up that subject because you have kind of made it interesting. That is very interesting what you have done. Thank you. I appreciate it. And I'm sure many people do. Thank you. I'll keep on the good work.
Wonderful.
Thank you. Thanks so much.
And Harold, thank you as well. Yeah, this is intriguing. I've been a fan of higher dimensional theories for years. Everything Harold mentioned, Kaluza-Klein theory. You were talking about 24-dimensional space-time. One of the things that people who do a lot of mathematics have told me is that when you add higher dimensionality to these, the physics just drops out a lot of the time. It just falls right into place, and and so for me, that's always been really intriguing. And I know that it's done some work as well. Eric Davis, back in like 2006, I think, did the first applied physics for string and brane theory. And he actually, the Alcubierre warp drive was one of his first papers. There was that, and then there was gravity modification. And he expressed, if I remember right, he expressed the same thing. He said these problems were so intractable, using normal physics, and then you move them into higher dimensional space, and all of a sudden they just drop into place. So, well, let me go to Mark Sokol next, sir.
Yes, Greg, love the presentation. One thing I wanted to mention, and this is just my understanding of Einstein's relativity theory, that when you're traveling at the speed of light, time slows down. So from the photon's perspective, it's actually leaving Alpha Centauri and reaching your eye instantaneously. So if you're actually able to travel at the speed of light and time would come to a stop, you would go wherever you're pointing it, or until you slow down instantaneously. As far as slowing down time, so the speed of light is really just a derivative of the epsilon and mu, the permittivity and permeability of space-time, which are how elastic space-time is, how much magnetic force it can maintain, and how much static electric force it can maintain. Those are actually variables that we can change by stacking electromagnetic fields on top of each other in the near field. I think this is what many previous presenters have been doing, making warp drives, quote unquote, and they should actually change time in that field as well. I know that they're able to curve light. They're able to pull objects in and out, and this is by creating standing waves of electromagnetic energy. Do you have any comment on that?
Wow, huge subject, and stacking electromagnetic fields to create a warp drive. I wish, Mark, I knew more about warp drives. Again, I think that I think it's possible. I don't know exactly how. I would have to really take some time to think through how that might work within the constructs of relativity. I do not want to get in an argument with Einstein. No one ever fares well that does that. And let me, my earpiece just dropped out. But yeah, I again, that's something I would have to think clearly through. Now, how does this fit? How does this overall approach fit within relativity? I think it fits quite well, but again, I have not formalized that. So that is a question that needs to be looked at a little more carefully. I notice do you have a screwdriver on that bench over there? I'll melt it for you if you guys invite me to your lab. I'll go do that. So
melt it with what?
Yeah, I assume you've got electric current around there somewhere. So
we have a lot of power.
No,
I have a 15 kilowatt power supply here that goes up to 12,000 volts.
Yeah, what I could do with that. You have a remarkable lab there, and in last week's presentation, I was quite. In fact, I was thinking of you when I added that thing about melting screwdrivers. I could do that easily. But again, according to your question, this is the relationship between a 10-dimensional space-time and a relativistic, within a relativistic structure is, they're going to be compatible. I think it's compatible, absolutely. But the formalization of that compatibility is something that's going to have to be worked out. And I have not done that yet. There may be somebody in the audience that's a lot smarter than I am that might be able to answer that question, but and take a broad brush and say, hey, this makes sense or it doesn't make sense. You know, I don't know, and yeah, it fits within a relativistic concept or construct, or it doesn't. But I'll leave that to someone else. Again, you know, I could use the help if anyone out there wants to pitch in and answer that question.
Also, the 10 dimensions of space-time that you're talking about, how does that work exactly? How many dimensions of space-time are we experiencing right now, according to that part of the theory?
According to what I presented today, you're experiencing 10. You just don't know it because you can't. There's no way for us to be able to determine at that level, in other words, at those that, you know, we talk about Planck time differences or even multiples thereof. I mean, until we get way up there, until that denominator becomes really manageable for the way that we can detect motion and movement. If you can see Planck time, you let me know. That's great. Mm-hmm. And maybe the world appears in three. You know, how does, hold up one finger and you say, all right, how many fingers do you see? I see one. But well, depending on how close they are to my eyes. But question would be, how many do you see? And if you see 3, then you're great. That's good, I would assume. So
I mean, really, we're living in 4 dimensions of space. We have this a little, the dimensions that they teach you in school is a little wrong, because 1 dimension of space should be a dot, just a location, like an electron, right. Just a dot. And then right. 2 dimensions would be a line, 3 dimensions would be a picture, 4 dimensions would be an object. So in space-time, or in time, we're actually doing the same thing. We're only living in the now. There never is yesterday. I mean, you can have
Right,
a
Mark. Right.
party
What I
for,
would say then.
for time travels. We'll have it last week.
Well, Mark is rocking the boat, but you know, Mark, if I could interject for a moment,
Sure.
see, one of the challenges is, mathematically speaking, I would tend to look at it the opposite way. When you get into dimensionality, you're talking about mathematical measurement of things, right? But one of the things I've always wondered is, in space, we don't really have one dimension or two dimensions. We live in, I mean, we call it three dimensions because of the way that we measure it. But then I've always wondered, are we conflating a legacy measurement system with an actual description of the space, right? Because, you know, the space that we live in is this volumetric three-dimensional thing, but that's the way that we measure it that gives us three. And I've always wondered, since that goes into the mathematics, are we artificially confusing the mathematics by adding three dimensions where maybe we only need one?
Right.
Also, when it comes to time, we're living in the now right now. But when you talk to people who've had near-death experiences, they're experiencing that one dimension that we talk about, you know, or the two dimensions where you can go back and forth on your timeline and see different aspects of your life from past lives and future lives all together. So I think that really our brain is a filter. We're getting filtered down to this one dimension of time, but in reality, all of those dimensions of time are happening together. And if you take enough 5-MeO DMT, then you'll see all 10 of them.
Mark, let me add one thing. And to answer your question this way, Mark, if I were to answer your question, you know, do we live in four dimensions? In our present moment, in that instance, that moment right there, yes, that was part of the presentation. Because you're not aware of, and we're not seeing the past corrective or the future predictive. We're not there. We're where we are right now. In the overall scheme of things, I'm saying that we live in basically a 10-dimensional space-time. But what we experience is going to be four-dimensional. It will be time, as well as three dimensions of space. So I hope that helps.
Okay, thank you.
Wonderful.
Thank you. Thanks.
Mark, thank you, sir. Let me go to William Alec next. Bill, sir? I think Bill may throw in scalars. I think Bill's going to throw scalars in here.
Later.
Later? Okay.
Yeah. Yeah, I just want to mention to Greg, you know, a very interesting presentation. I don't know, to me, there's a strong correlation between time and gravity. Okay, very strong. It's like they're one and the same. And the reason why I say this is that, you know, I spent a lot of time studying this phenomena at Santa Cruz. You know, it's called the Santa Cruz Mystery Spot. Now, the local school there, U of C Santa Cruz, you know, they would take field trips to this place, you know, have students looking at this phenomena, but they would always write it off as an illusion. What you're seeing really isn't real at all. But, you know, the time that I spent there, I found out, you know, this thing is for real. Okay. And what I mean by that is that it affects the tick rates of clocks. Okay. Now, there's one guy that wrote a book. His name is Douglas Voigt. He wrote a book on these mystery spots. And he took a crystal, an oscillating, a multi-megahertz crystal, and walked it into the phenomena, and the crystal would start slowing down in its tick rate. Okay. Which means that the gravity in there is increasing. Now, if your tick rate would speed up, okay, you would have less gravity, okay? So, yeah, I can follow along with that. But see, what Douglas did is that he had a clock on the inside and the outside of the phenomena, and that's how he observed the difference in the tick rate. So I did the same type of experiment, but I used an Accutron watch, okay? And I discovered that, yes, the tick rate slows down as you walk into this phenomena. And it also affects, there's appears to be a gravitational change there as well, okay? Because the two are strongly correlated. and the tick rate would slow down, but you would also observe a shrink phenomena occurring. Now, when you're inside the phenomena, it's like you don't really see a difference at all or feel a difference, but yet you can actually see it. So in other words, light would follow like maybe a geodesic pattern, but it also would affect the height of material objects as well. So there seems to be a strong correlation between time and the effect of gravity and how it affects matter, that you observe the shrink growth phenomenon occurring.
Well, and Bill, if I can interject, some of that, because I remember back when you measured the gravitational mystery spot, I think there are a couple of challenges there. From what I remember, and I could be mistaken, but the one in Santa Cruz, it's like a massive heavy meteorite or metal deposit under the ground. And so you actually do have a real gravitational disturbance. So you were doing measurements on that, but then the other issue, I think, is they've kind of turned it into a tourist attraction. And so you've got almost like these carnival show. And when you talk about the shrink growth phenomena, I think that's one of the challenges where, again, this tourist aspect of it, they've tilted their buildings and created strange rooms and perspective stuff. So there's the impression that I got was there's a lot of confusion, and you have to kind of tease apart the actual phenomena from what people have kind of done to accentuate that, you know?
Right. But they also do like little experiments there as well. You know, they have a swinging weight, and then you look at the shrink growth phenomena, you know, as you approach the center of the phenomena. Okay, it also affects the height as well. But, you know, all that I want to say is that there just seems to be a strong correlation between time and gravity. You know, that's basically all that I wanted to say here.
Well, interesting. Yeah.
Thank you, Bill. Let me go to Michael Boyd next, who actually has a Santa Cruz mystery spot poster on his wall behind him.
Hello. Yeah, I was going to say that, Bill. I got it right behind me here. Santa Cruz mystery spot. That's where I am. Santa Cruz County. I live in Sokol, California. So it's about a mile from me.
Well, 20 years ago, I did spend a lot of time there. So it was a while back.
I've been here for 21 years. So Greg, my question is about, I have a couple questions. The first is, do you think gravity is linear with distance always, or is it non-linear depending on the distance?
Wow. Okay. I believe that, what's the best way to put this? I believe the gravity is constant, certainly throughout the universe, and that's been shown to be the case. Although you hear some individuals talk now, and they're beginning to say that perhaps in certain areas of the universe, the laws of physics may change or differ. And it's really cutting edge stuff. But I don't know, and gravity is such a personal subject to I think every foundational physicist out there. Wars have been fought over this, just about, you know. And I do not have a proper answer for your question, Michael. I don't. I wish I did.
Just to give you the context is,
sure.
So acceleration's distance squared over time squared.
Right. Understood.
So that's when I'm saying it's linear.
Right.
I'm asking, is it always distance squared over time squared? That's the question.
Is it always that way? Again, I cannot answer that question. It would seem reasonable that gravity would always carry with it a standard, regardless of where you were or within the number of spatial dimensions that exist, whatever those may be. Again, we're speculating here, but I think it's constant. But at the same time, there is always the possibility that it is not. And I hope I'm understanding your question properly.
No,
I may not be.
You are.
But
I think you are. So I appreciate that answer.
Sure.
The other, do you know what, have you ever heard of the phrase offset spatial divergence?
Offset spatial divergence. I could guess, but go ahead and enlighten me.
So basically what it is to travel in time is to travel in space. So
that's interesting. Okay.
Because if you think about it, everything in the universe is moving, correct?
That's correct.
So if you're moving in time, you have to move in space then, right?
It's interesting. Yes. Okay.
So so now in general relativity, they talk about the warping of space-time. You kind of talked about it a little bit about how you can slow time. Basically, that's a natural phenomenon that occurs. You got a GPS on your cell phone. It's connected to a satellite. The satellite in space, the time is going faster than it is here on the surface of the Earth where you have your cell phone, because of frame dragging, essentially, because time is slower at the surface of the Earth than it is in. So is that what you're talking about?
No, I think, and again, I think you're getting back into relativistic time, which I have no argument with. I think, again, I refuse to get in an argument with Einstein. That never works. But I think that you have to stop and you have to look at time as being the carrier of space and not space as being a place where time happens. And so when we get into frame references and that type of thing, that is, I think, is a different argument altogether. It would be an interesting thing to do, basically, is to go back and say, all right, let's meld these two together. Let's take a look at relativistic time frame reference, and let's then meld that back into a theory of 10-dimensional time. I have not done that intuitively. Again, I refuse to argue with Einstein. Not going to go there, but I think that there may be a way. There has to be a way to relate.
Well, I have heard of 11-dimensional time, but I don't think and I've heard of 5-dimensional. So I kind of don't. I'm having a hard time grasping that. So I'm trying to get it from a different approach. So if basically you agree, though, that time is slower on Earth than it is in space, right? I'm
going to agree that the way that we experience time is, again, relativistically, is in line with exactly the way that relativity says it should be. If I'm, without going into a lot of detail, I believe that relativity is right on. I believe that, yes, there are different ways that we experience time. But again, I think that this can be tied back into a 10-dimensional space-time, Michael, I believe. Now, I have not formalized
I actually agree with you.
Yeah.
The part I'm feeling a little uncomfortable is there's you need to look at it from both sides, from the the condensed space, or what I would call condensed space-time on the surface of the Earth, and expanded space-time, which is in the outer space in this case.
Right.
So and when we're talking about expanded space-time, then we're not talking about gravity anymore. We're talking about anti-gravity. And if that's the case, then wouldn't that suggest that time's pushing back? So basically, when expanded space-time, time goes faster, the length gets longer when you go the other way. So think of it, you're like traveling in near the speed of light in a spacecraft heading out into deep space. And then there's offset spatial divergence. If you go out for a light year, and you come back for a light year, time is like all your relatives are gone. Okay. That's offset spatial divergence. So, but it also goes the other way. If you're like accelerating to the speed of light and you're heading towards the sun, or maybe like those UFOs that are going in the volcanoes, you know, it's heading down towards the mass. It's the same effect. It's the offsets, but in that case, you're getting, the time is getting condensed, right?
Well, in theory, if I remember right, from what I've read, time passes 6 to 7 times more slowly on the surface, if there is one, of Jupiter. I remember reading something about that. They've said when you get to the center of mass of Jupiter, simply because of the increased gravitational field. So for me, this is something I personally, this is kind of beyond my brain cell capability. I always struggle with this. The other thing that I kind of struggle with, I probably shouldn't, is the clock offset with the GPS satellites too. I mean, they're higher up in the gravity well, and so time passes more quickly for them, and they have to do an offset. I'm like, how, I don't know. Conceptually, I struggle with that.
So what I'm trying to suggest, Greg, is I agree with the path you're on, but I think you're missing half of it. Okay.
Okay. Fair
and I
enough,
think,
Michael,
but I do think
enough.
it, but I do
Appreciate
think
that.
it's a valid approach, and it's, you know, just look at it from the other way too. Look at it from both sides always.
Okay.
That's how I try to do it.
Michael, I appreciate it. I mean, any constructive criticism is welcome. I appreciate that. Thank you.
And
Okay,
Michael,
thank you. I appreciate your comments and your answers too.
Thank you very much. You know, the other thing, if I could mention it really quick, was I should write the name of this show down. It pops back into my head so often. It was a show, it was an interview with Dr. Lisa Randall and Brian Greene. It was on higher dimensional space-time. It was on the Science Channel. This was back in the 2000s. And what they suggested was they were trying to do a representational model of brain theory. And they showed these membranes, right? They look like big orbs or you know, glowing balloons in space. And in that case, what interested me about it was they said that the premise was gravity is so weak in our universe because we are located on the electromagnetic brain. And they said the electromagnetic brain is primarily here, and where the EM brain and the gravitational brain, where they overlap, is our space-time, but we live on the EM side of that. And so they were postulating that there was basically a parallel universe, presumably, that's primarily in the gravitational one, where those forces would be separate. The thing that interested me about that, though, was, and they didn't highlight this in the show, was they showed, so again, if electromagnetism is one brain and gravity is another brain, where they showed them moving together and overlapping, time would still be the background. So in their model, time was dimension 0. Time was the base dimension that everything else happens in.
Interesting.
Well, yeah. So again, let me for questions, and we're getting in pretty deep here today. But it's Option Y on Mac or Alt Y on Windows. If you have any questions for Greg Cathcart. Greg, I genuinely cannot thank you enough for this presentation. This is inspiring and incredibly in-depth material. So,
thank you. Thanks. Thank you, Tim. It was a pleasure. A lot of fun.
Oh yeah, yeah. No, this is one of those ones to go back and just rewatch the presentation and try and fit all of those pieces together.
Yeah.
So, how many years have you been working on this for?
Just, you know, Tim, it comes out of a lot of research that I've done over the years. It's impossible to say that there was a starting point and then a finishing point. I would say that a few years of reading, getting out there and looking at what is happening in research, kind of culminated into this presentation at this point. Hopefully that will grow as time goes on. I appreciate Michael's comments, and I knew there would be a challenge with this from interpreting it from a relativistic structure, and because that's our fail-safe point. That's where we go to look at things, because it's essentially the way that we have all been trained, or at least the physicists certainly, and others have been trained. But it will be interesting to see how this matures over time. And this is why I strongly urge and would appreciate any constructive criticisms from the listeners of this presentation of this program today, to come back and say, hey, have you thought about the following? This individual that emailed me this morning, the thing that I so appreciated about what they did was they sent me an email that must be on my phone. It had to have been 10 pages worth of critiques and questions, and how does this fit in within this reference? How does it fit in with this particular theory? And that is all great food for thought, and it's a great starting place for so many other directions that this might go.
Yeah, no, I mean, that makes sense. There's so much depth here to this, and it feels like with your presentation, but also a lot of the others that we have, it feels like we're just pushing against the limits of these models. That's a big part, is like we science has developed these models, and we're just kind of reaching the end in a lot of cases, but we're not really sure where to go next. So let me go back to Mark. Mark has his hand raised again. Sir?
Yes, and this time a question is coming from the YouTube live stream over by the Alien Scientist channel. Dretcore Original is asking, traveling back in time, does it create a parallel or self-fulfilling future, or both? Parallel timelines or alternative timelines.
Okay, that's interesting in that I have not really taken the time to take a look at parallel timelines. I would say this, that essentially what I presented, if you go back and look at the CTL, there is definitely the possibility of multiple realities as far as I interpret this. Are there possibilities for differing timelines within the same reality? And I assume that's the question that's being asked. That is a great question, and I've not really given that a whole lot of thought. I don't know, and I don't know if there are loops that are opened and then closed. And I've read through quite a bit of fascinating perspectives on how multiple timelines exist. Now, I would say this from the standpoint. Go ahead.
Have you heard of the Mandela Effect? That's an interesting thing.
The Mandela Effect. Where were you the day that Mandela, got out of prison or whatever?
Oh no! Well, some people remember him dying. Some people
remember him. Yeah.
Remember him dying. Remember alternative universe. And I've actually had arguments with friends of mine, girlfriends, whatever, where it seems like we're coming from alternative universes. They're adamant they remember something, and I am positive it didn't happen. And the only solution to me is alternative universes there.
I'm gonna have to resort to Occam's razor here, Mark, and say, look, there has to be a psychological perspective to this, and I'm not talking about that in a negative way. I mean, we are all of us are fooled with our own perceptions and memories, and it's easy to remember things that we can create even subconsciously, and we can come back and say, yeah, that happened. Is it above my pay grade to say absolutely that can't happen? Yeah, it's above my pay grade. I'm not sure whether that happens or not, but I would say that it's probably, in my opinion, I could be wrong here, but it is probably an artifact of our own psychology.
I would agree. I would agree with that. And it's one of the things, this is kind of an aside, but one of the things that has intrigued me, and this comes out of UFOs. This is absolutely UFOs. I think one of the most important and least well understood phenomena is mass hysteria in the human mind. And like the Mothman prophecies, right? With the movie with Richard Gere was a perfect example of that. Another one is, UFO reports, not just UFO reports, but the fact that when you have times of increased tension and stress, right? Like the pandemic, things like UFOs, all of a sudden they pop back up over and over again. And so these things are tied, they're tied into our psychology, they're tied into anxiety, they're tied into uncertainties. And unfortunately, I think as a society, we don't study them enough. You get into the phenomenology of The ghost hunters and stuff like that would be another example of it. You get into this phenomenology of the paranormal, and it's understood that psychology plays a role, but it's not well understood why or how, so.
That's a good point.
Yeah, it just, that's always intrigued me. One of the things, and again, I'm going off on a tangent, but I used to commute in Seattle across the 520 bridge. And so one of the things that I noticed was this was a Malthusian thing, where the worse traffic got, the closer to road rage people got, right? Consistently speaking. Which shouldn't be a surprise, but and so when you have relatively smooth flowing traffic, people drive relatively normally, and when that starts to get packed and it slows down, people start to act screwy. They start to take risks that they wouldn't normally take, and they start to do stuff that you look at it and you go, okay, this person's not behaving rationally anymore, and I always looked at that and said, in some ways, it's like we're all frogs in a pot of boiling water, and maybe it's a different temperature, and we all have a different tolerance for it. But yeah, there are just so many different factors there, and unfortunately, I think in science we don't take those into account enough.
Agreed.
Let me see. So let me see if there are any other questions. I think we're all set. So let me do this. We're about 5 minutes from the top of the hour. Let me put this thing back on gallery view. Everyone, please give Greg Cathcart an enormous applause again for his Q&A session.
Thanks, guys.
And a wonderful,
thank you,
Greg. That was absolutely tremendous presentation. Thank you so much. If you ever have anything like that you'd like to share again, please bring it back here. Please.
I will. Thanks, Tim. Be glad to do it. Thank you so much for having me.
Oh, absolutely, sir. Absolutely.